All right, so here we are adapting to the new way we'll run the class for a couple weeks. Again, the date we will be canceled through is till March 27th. That's 2 weeks from now. We're going to try to keep the class going at the same pace. If that doesn't seem to be working, then we can change the way things are going. So we'll just jump right into it. So we're talking about Chapter 4, Basic Physics for Radiography. We talked a little bit about this stuff last week, talking about a little bit about magnetism, electromagnetic energy, and then the basic portions of an atom. The picture here kind of shows you a zoomed in version of an X-ray tube itself. So from week 1, we talked about a tube housing, kind of a lead lined box that holds in most of the radiation. When we make X-ray, it goes in every direction. So you can see it's entering the glass envelope going in every direction, and then we have a portion of the X-ray beam which is useful, which is this portion traveling directly down. So cathode and anode, we'll go over the cat and an word prefixes that we'll use going forward. Cat basically means negative, anode means positive. So we're taking a negative portion with a bunch of electrons, slamming it into a metallic disc on the other side, and then that kinetic energy from the moving electrons turns into electromagnetic energy in the form of X-rays that we can use. So when we talk about basic physics for radiography, we have to talk about a few basic underlying principles that kind of govern how we are able to do things. The first would be matter. So when we talk about matter, it's anything that occupies space and has shape or form. All matter is composed of atoms. There are elements from your periodic table from chemistry, whether it's high school or college, where you're going to have different numbers of protons in the nucleus of each atom, and that's going to determine what element it is. And then we have 3 basic forms of matters. We have solids, liquids, and gases. Gases take up the space around you. Liquids take up the shape of whatever container they're in, and solids maintain their own shape. And then opposite of matter, but kind of meaning the same thing, we have mass, which is a quantity or amount of matter that makes up any physical object. Mass can also be considered weight, but weight is a little bit more dependent on gravity. Mass is an absolute value. So if you take your body weight and move it out onto the moon, you're going to technically weigh less because you are having less gravity pulling your body down to the center of the moon than you do on the Earth. But your mass doesn't change no matter where you go. So what we have right here, and this is a little misleading, I'd like to delete weight right here, but it's too late now. An object may change its form, so we can move between these states of matter, but its mass is unchangeable. So cannot change mass. You can cut off your hand, but your body with the hand still had the same amount of mass. You're just a body without a hand if you cut it away. It's the same quantity of mass. So a little bit more on that concept. An object may change its form, but its mass is unchangeable. Our example, a 20-pound bucket of water may freeze into a 20-pound bucket of ice, or it may evaporate, resulting in 20 pounds of water vapor. 20 pounds of water vapor is an enormous amount. But these two things are a little bit more easy to think of. Maybe 2 gallons of water that you think of in jugs. So the forms are changing here, but the mass remains the same. And then we have some laws that kind of govern the way that we do things and the way that we consider these concepts. So conservation of mass and energy. Conservation is the concept of retaining and not changing. So matter can neither be created or destroyed, but it can change form. So everything that's present here on Earth is already here. It cannot be created, cannot be destroyed. We can take it, we can make other things, we can change its form and things like that, but we cannot make new matter and we cannot destroy any current matter. Second one, and this is kind of the one that really makes a big difference in what we're doing here, is energy. Same concept, can neither be created nor destroyed, but it can change form. We'll talk a lot about the different forms of energy along the electromagnetic spectrum, and then some types of energy. We talked a little bit about that last week as well. And when we consider matter, we consider the very base underlying single units of them, and we call those atoms. So an atom has a nucleus the same way a cell does, and then that's made up of the positive and neutral particles in the middle, and then we have some negative particles floating and spinning around the outside, similar to how the solar system works. So We call atoms the building blocks of different matter. There's tons of different subatomic particles. The ones we'll key in on here are going to be the electron, proton, and neutron. They each have a charge, which is an important part of how they function, so we need to know those. We need to know P for proton is positive charge, N for neutron. Actually, the whole word root, it really kind of correlates with neutral pretty well, so neutrons are our neutral charge. And then our electrons, not really a very great way of memorizing that, but they're the odd one out, so they're outside floating in orbits around the nucleus. And they have a negative charge, and that's important. And then the nucleus is the center of the atom. The center of the atom, you can see in this circle here, contains the protons, the positive subatomic particles, and the neutrons, which are the neutral subatomic particles. In most cases, they are an equal amount. So neutrons pointing to the red ones, 1, 2, 3, 4. Or protons pointing to the blue ones, 1, 2, 3, 4. We would say this atom is stable in its nucleus because it has an equal amount. The thing that we're going to see is that a lot of atoms don't have an equal amount of protons, which are the blue ones, 1, 2, 3, 4, and electrons, which are the green ones, 1, 2, 3. So we have 4 positive charges here and 3 negative charges, meaning this atom has an overall positive charge. It has one more positive subatomic particle than it does negative. And that's going to be important when we talk about bonding atomically, because negative atoms and positive atoms, ions we'll call them, are going to want to be near each other just by the basis of their magnetic attraction. And we'll talk about that a lot here too. And then an important concept to determine what element we're talking about is going to be determining how many protons are in the nucleus. So an atom with 4 protons in the nucleus is actually an atom or an element called beryllium. If you add extra protons to the nucleus, which is very difficult, you get a completely different element. So 1 proton in the nucleus is hydrogen. If you put a second one in there, what you get is helium. And then you move up, you throw a third one in there, you move on and you have lithium, and then now we have beryllium with 4. So those don't typically change. When they do change, we have an entirely new element. I'm going to move on here just because this is going to get too complicated when we're moving forward. So talking about the relationships of matter. I really like this graph because it kind of gives you a sense of the relationship, almost like a Venn diagram, where each thing fully fits inside the others. So subatomic particles, our protons, our neutrons, our electrons, make up atoms. Atoms binding together make up elements, and then a group of elements or elements together make up matter. Another thing that can happen when atoms combine is they can form molecules or compounds. There's a minor difference between the two. A compound is a molecule that contains 2 different atoms. A molecule is 2 or more that have the same. So a molecule would be like oxygen, where there's 2 oxygen elemental atoms binded together. A compound would be something like water, where you have 2 hydrogens and 1 oxygen. So, talking about atoms a little bit more, I said this a little bit on the first one, so we'll just kind of move through this quickly. When an atom is in its neutral or natural state, it will have an equal number of protons and electrons. So this would be a neutral or equal state atom. So still beryllium, 4 protons in the nucleus. And then now what we have is 4 electrons as well. So a neutral atom with no charge. So we say that's balanced, stable, or neutral. Any of those words are fine. When an atom loses or gains an electron, and we only say loses or gains an electron because that's typically how this works. We generally don't change the amount of protons or neutrons because that can significantly change the way that the atom functions. So we talk about losing electrons to generate ions. So when an atom loses or gains an electron, the atom becomes unstable because of the uneven or odd number of electrons. It is now called an ion. When we lose an electron, that means there's more positive charges than negative. It becomes a positive ion, or an anion, if we go back to the first slide. And then if we gain an electron out here, a third electron floats into this second shell here, we end up with a cation. Cat is the word prefix meaning negative in this situation. And then the process of losing these electrons we call ionization, where a neutral or balanced atom gains or loses an electron. it becomes ionized. And then the amount and the way that electrons are distributed into the orbits around the nucleus is going to form somewhat like the solar system works, where there's an orbital, and the first planet in the solar system, Mercury, only inhabits this close orbital. It stays close to the sun or the nucleus. And what we call that here is a shell. So electrons occupy orbits around the nucleus that are called shells. So this atom has 4 shells. It's not clear what it is because there isn't a number of protons here. And we name them alphabetically. This is important. The one that we really care a lot about is this K shell, or the inner orbital, the closest one, where Mercury floats, if that helps you remember. And they're named alphabetically. And they go up. There's only certain elements that are going to have a certain number of orbitals, and the amount of electrons in each orbital increases the further you get away from the nucleus. But they're named alphabetically. So inner shell is always K. So it's LMNOP. I do think there is an extremely large atom that has a Q shell all the way on the outside, but I'm not certain. So we call these shells, K shell being very important. So this illustrates them a little bit better. You can see as the number of shells increases, the amount of electrons they can hold increases. Another important concept, the K shell, that inner orbital right here, the first one in the nucleus, only ever has 2. And one of the ways we make X-rays is to knock some of those electrons out of their orbitals, and that's going to always come from the K shell, so that's an important one. Most of the elements we deal with don't go much past the N or O shell, so we won't really worry about P or Q for now. So binding energies. So we're talking about atoms. Again, we move back to how badly do they want to be together. It's the same concept with KVP. We increase the energy level of the X-ray. How badly does it want to get through the patient to the image receptor? It comes back to magnetism. So like charges repel, meaning 2 positives are going to push away from each other, kind of like you see here. And then opposite charges attract. So protons and electrons, which are negative and positive, are going to want to be near each other. It's the same concept here. So if an atom is a negative ion, meaning it has 1 more electron in its orbitals than it does protons in its nucleus, it's going to want to be near a positive ion, which has 1 less electron in its orbital than it does protons in its nucleus. So these are going to move towards each other, and that's how some of these atoms are going to bind or bond together. So magnets are a really good example on kind of a large scale for what we do. And so going back to the shells, the further you get away from the nucleus, the attraction between these negative electrons and the positive protons in the nucleus gets weaker just based on distance. So you can see this electron is going to be binded more tightly than the one next to it, and the one further out, and the one further out, and it's going to get less and less and less as we go out. So different shells have different binding energies just based on how far they are from the nucleus. And larger atoms, meaning more protons in the nucleus, are going to have higher binding energies because they have more protons in that nucleus that are pulling our electrons closer and tighter together. So the binding energy is the highest at the K shell. This is incredibly important. You really want to pick up on this and try to remember this. We call this strong nuclear force. It's essentially this positive-negative attraction between protons in the nucleus and electrons in the K shell, that initial shell first. So strong nuclear force is the positive to negative attraction between the nucleus and the electrons in the inner orbital, or the K shell. And so the K shell is the most important in X-ray production. Why is that? A lot of the times, the main way we're going to make X-rays actually doesn't include this, but X-rays are produced by knocking out K shell electrons in a pretty complex way. We'll talk about that in Chapter 5 in detail, so I'm not going to bring it up quite yet. One atom that we really like, and as you can see, we're starting to get KLMNOP shell, so getting way out there, is tungsten, whose atomic symbol is W. We're going to go into tungsten a little bit more detail, but sometimes questions you'll come against will have to do with what the atomic symbol is for tungsten. It's going to be W. Doesn't make sense. Lots of them are pretty close to what their actual name is. Tungsten doesn't fall under that model. So it's important in the production of X-rays because what we make our anode or our X-ray target, or if we go back to the first slide, we're shooting electrons across the gap at this target. We make this target out of tungsten, and we'll go over a couple reasons why here. The filament also, if we go back, I should have said this a second ago, is this part where we're going to make these electrons to shoot them across this gap. That's also made out of tungsten. Mostly because tungsten, it does really well with heat. It can withstand high levels of heat. If we go back to the first week again, that X-ray production process is very inefficient. We generate 99% heat and only 1% X-ray. So 1% of what we make in this process is X-ray, which is very inefficient. So we are generating a lot of heat. And what tungsten is really well made for is it has an extremely high melting point and it can withstand extremely high levels of heat. So going over why we use tungsten, it's kind of a complicated answer, and we need to do just a little bit of chemistry to make sure we know why. Tungsten symbol is W again. Our atomic configuration. So configuration describes what are the numbers that tell us how many protons and neutrons are there in the nucleus and how many electrons are in the outer shells or orbitals. So mass number is the first one we talk about. Mass number is 184. It's not the atom's mass, or it is, sorry, this is the atom's mass or weight. And the way that we determine mass number is we take the number of protons plus the number of neutrons in the nucleus. Electrons don't weigh enough to count for the atom's mass, so we don't consider them. Protons and neutrons are significantly heavier. So what we have with this atomic number is describing how many protons are in the nucleus. So that's an important portion of what we're doing too. So if we pull up an image of the periodic table, what we get is these small numbers in the corners. Make that a little bigger. The small numbers in the corners of each one tell you how many protons there are in the nucleus. And that's our atomic number. So starting with hydrogen, 1 proton in the nucleus. Helium, 2 protons. Moving forward, 3, 4, 5. Carbon, nitrogen, oxygen. I don't know that one. Up to 9, 10. So the atomic number is the number of protons in the nucleus. It's an important part of what we're doing. And so tungsten finds its way all the way down near the bottom at 74. So W for the symbol, and 74 meaning the number of protons in the nucleus. So what we have is an atomic number of 74 and a mass number of 184. If we go back to what mass number means, it's protons and neutrons in the nucleus. What you can tell is if you subtract our atomic number from our mass number, it tells us how many neutrons there are. This is the abbreviation I use for neutrons. It's N. It would be superscript 0, 0 to show that it's neutral. And we subtract our atomic number from our mass number, and we show that there's 110 neutrons to our 74 protons in the nucleus. And that kind of just goes along with the ability to withstand heat and its ability to take those electrons as they come across the gap from the cathode and stop them and turn them into X-ray. So another very important concept dealing with binding energies. Now we're actually quantifying binding energy here by saying how many, and these are kilo electron volts, not something you'll need to worry about right now. But the closer we are to the nucleus, so moving down from our outer shells, PONMLK, so that K is the inner shell, the one closest to the nucleus, only has 2 electrons, but they have an extremely high binding energy relative to the others. So as we move out away from the nucleus, from the K shell, it drops to about 15 to 20% of our original binding energy. So these K shell electrons want to be near the nucleus very badly. As we move out, that gets less and less, out to the point at the P shell where they're barely even held there at all. So important relationship here. So we talked about relationships last week, inverse relationships, one goes up, the other goes down. So as you get further away from the nucleus, KLMN, our binding energy decreases. And then the opposite relationship, as you get closer to the nucleus, our binding shell energy increases. And then we'll talk a little bit about how atomic number relates to density for structures. We have some x-rays over here of the abdomen. Unfortunately, I know we don't x-ray abdomens as LPTs, but they generally produce some of the most interesting x-rays. So again, we have 118 total elements. Some of them are man-made. The ones that are man-made generally are held off in a different portion of the periodic table, and then a couple of them sit at the bottom down here. So 118 of them, we only show a couple of them. These ones are named for basically what number they are in Latin. So this 110 is unium. It's kind of a goofy name, but we have 118 total elements, and then they're determined by their atomic number, what they are. So calcium, which makes up kidney stones, as you can see in these pictures, kind of all over the place, some down in the bladder. A couple of these might even be in vasculature down in the common iliac arteries and veins. And then bones as well, kind of make up the pelvis here. This is a child's pelvis. You can kind of see the growth plates. This is an adult pelvis. There's no growth plates, solidly formed bone. Not a very healthy looking spine in this area. So calcium has a fairly high atomic number relative to what we normally look at. We are carbon-based life forms. If we think of bone as hard, we have calcium here at 20, carbon here at 6. So most of our soft tissue is carbon-based. So it's about a third the atomic density of the rest of it. So that's why we're going to see bone a lot better, because essentially the higher the atomic number, the relationship here that's important at least, the higher the atomic number, the greater the element's density and mass. And the greater the element's density and mass, the more likely it is to absorb or attenuate X-rays. So moving up from calcium, we have lead, which makes up bullets and shields that we use for X-ray. And this is what you can see in the child's stomach. He got his hand on a nice high caliber bullet there. So that lead bullet inside the body is easier to see on an X-ray than a kidney stone. So it stands out a little more than these kidney stones down here because the lead has a much higher atomic mass than bone does. So bone's kind of grayed out roughly in here, but this bullet, which has a really high atomic number, is very white, very bright because it absorbs a ton of X-rays. So relationship here, the higher the atomic number, the more likely it is to absorb X-ray. So now we'll talk a little bit about energy. What we just covered was matter and kind of atoms, subatomic particles, and then some basic principles for atoms and how they work. Moving on, energy is our ability to work. It occurs in several forms, and again, moving back to our law of conservation of energy, it can be changed from one form to another, but it cannot be destroyed or created. So heat is a type of energy, thermal energy, light is a type of energy, electrical energy is different. We went over this a little bit in our preview lecture, but anything in motion has mechanical energy. Chemical energy is anything that is stored energy inside of chemical bonds. So when you eat food, those bonds break, your body can take the nutrients in. When you pour gasoline in your engine, it doesn't have any innate energy, but when we light it on fire, it can produce a lot of mechanical energy, getting the car moving. Thermal energy, you can take and use to heat your home. Nuclear energy is powering things with releasing radionuclides, which is unstable atoms that have their nucleuses decaying and shooting off protons and neutrons. Electrical energy is the concept where current moves through wires, and that's a type of energy. And then potential energy, this is more of alternating current. This is more of direct current or batteries. So potential electric energy talks more about having those acidic batteries that we use to store electrical charge. So that's potential electrical energy. And then the big one, the one that we talk about that most, that matters the most to us, is going to be electromagnetic energy. So it has properties of both electric properties and magnetic properties. So what we're talking about is wave energy. So it travels in these types of waves up and down. And the higher we go, or the shorter the wavelength we go, and we're going to talk about this in a second, so don't worry about wavelength yet, the higher the energy it is. So X-rays and gamma rays are what we use in medical imaging, and they are the highest energy, but they're the lowest ability to travel. So radio waves, which are far on the other end, which have extremely long 1,000-meter wavelengths, are going to have a very long transmission distance. That's why we can hear radio in a car from a tower that might be miles away. But they have very long wavelengths. So electromagnetic energy travels in waves. So this is kind of a thing that we're going to keep coming back to. And it travels at the speed of light. This value right here is meters per second. It's something in the range of 5,000 miles per second if you divide this out. So miles per second is extremely, extremely fast. If you think about a car that only travels at 60 miles per hour. An hour is 3,600 seconds. So when you think about meters per second or miles per second, it's extremely, extremely fast. So by the time that you energize an X-ray tube and the X-rays leave the X-ray tube, go through the patient, and enter the image receptor, there's no way you could ever track them or watch them or see them. By the time that you've heard the signal on the machine that says that you've sent X-rays, they're already in the image receptor being processed to show you the picture on the computer. When we talk about an atom as the building block for matter, for our electromagnetic energy, the photon is our building block, with air quotes around it, for energy. So it's our smallest unit of electromagnetic energy. We think of it as a packet of energy that behaves like a wave and a particle, which is weird. Because waves shouldn't or don't interact with things. That doesn't seem this way here, because obviously the antenna in your car picks up radio waves. Microwaves transmit thermal energy to your food. Infrared you can feel. Visible light you can see. But we think of them also behaving like a particle because they can hit things and actually make changes, where light, you don't really think about it as interacting with things. So its particle form makes it seem like it interacts with things, whereas waves typically don't. These are incredibly important relationships. You'll see this slide again in our cumulative review at the end of the semester. So the average wavelength, talking about these right here, so this is a long wavelength. These are very short wavelengths. It means the distance between here and here. The average wavelength of a diagnostic X-ray photon is 1/billionth of an inch, so very, very short. And then that means an X-ray has high energy when it has short wavelength. And these three relationships of high energy X-rays are going to be important. So X-rays with greater energy have a very short wavelength. They penetrate the body better, so higher energy, greater penetration, able to pass through the patient. And they also have a higher frequency. So you're going to look here, wavelength, and here, frequency, and you're going to see an inversely proportional relationship. So as our wavelength gets shorter, which is a result of greater X-ray energies, you're going to have higher frequencies. And we're going to talk a little bit about that here. So amplitude, it kind of nice little graph shows you how each thing is labeled and what it means. The amplitude is the distance between the crest, this would be a crest, and the trough, this would be a trough, of the wave. It's basically the wave's height. It doesn't really matter for X-ray. We don't quite use this as a useful measure for X-ray. What we do use is wavelength and frequency. So wavelength is a measure of the distance from one crest to another. So crest to crest is one wavelength. And then frequency is the number of times per second that a crest passes a given point. So a crest right here, and we draw a line, and we watch the wave kind of wiggle its way across it. We look how many times does this crest pass our measuring line per second. That's going to give us a frequency. So the shorter wavelength photons, meaning higher energy, we go back to this one. So X-rays with higher energy have shorter wavelength and higher frequency. X-rays that are shorter wavelength will have more energy than longer wavelength and will be able to penetrate through more tissue. To measure velocity, we're going to multiply our wavelength times our frequency. These are always going to add up essentially to our speed of light, at least in this scenario. So frequency, a little bit easier way to look at it. Number of times per second that a crest passes a given point again. We're going to look at crests, again, the top part of the wave. How many times, we'll say this interval here is a second. How many times does that wave pass through this portion in a second. We're using actually the trough right here to measure it, so you can see trough to trough in 1 second is going to be 1 hertz. Hertz is the way that we measure frequency, and so this would be 1 hertz. Now we're kind of moving from a trough basically to a crest. On the next wave, that's about 1.5, so we'd say that's 1.5 hertz. And then trough to essentially trough, but we have 3 waves, 1, 2, 3, pass through this in a second, that's 3 hertz. So that's kind of how frequency works. It gets to the point where you can't even really see these at the points where we work with X-ray frequencies, and we'll get to that. So this is our electromagnetic spectrum. We had it on other slides, but it's going to look a little bit more friendly to you, make a little more sense now. We have a little bit of area here that we can actually see. So we have red on one side, violet on the other. So infrared meaning below red, ultraviolet meaning above violet. You have Roy G. Biv, red, orange, yellow, green, blue, indigo, violet is the way that we kind of say from a low frequency to a high frequency, how we can see visible light. And again, on really long wavelengths down here, we have radio towers, computers, cell phones, kind of as we get into microwaves. This is also how satellites communicate. Infrared, ultraviolet above it, and then X-rays and gamma rays, which are in the very, very high frequency, low wavelength portions. This part on the bottom, we'll talk about in a couple weeks, but essentially the longer the wavelength, shorter the frequency, they don't damage the body, but we reach a point in the ultraviolet area where we start to ionize cells. The amount of energy that the wave carries is enough to actually make changes in our bodies, and that's going to give us short-term exposure, instant thermal effects. We know that being out in the sun too much, portions of ultraviolet rays on the stronger or higher frequency portions can burn your skin. It's the same concept with X-ray and gamma rays. So at a certain point, electromagnetic energy becomes able to ionize your body, which is ionizing. If we go back to a couple slides ago, take me a second to find it. Sorry if anyone's epileptic. Ionization is the process of knocking these electrons out of their shells. So what this radiation does when we say it's ionizing radiation is it's able to knock these electrons out and make positive ions. Okay. So we use light a lot to demonstrate X-rays, whether it's shadows or otherwise. They have a lot of overlapping characteristics. So X-rays and visible light both are forms of electromagnetic energy, and they have similar characteristics. What they do similarly, and there's a lot less of these than there are of differences, but they both travel at the same velocity, which is the speed of light. They both have the same effect on intensifying screens, which we won't really talk about in this class. And they both can cause burns. So sunburn can burn your skin. Radiation burns are much more serious. There are differences in characteristics. X-rays are going to be able to pass through your body, while light will not. X-rays you cannot see, whereas light can. So if you look at a lamp, it's clear that there are light photons coming out of the lamp. But when you look at an active X-ray source, you're not going to actually see the X-rays. You're just going to see the light that represents where the X-rays are. That's our light field or radiation field that we talk about. That's actually a light bulb that's reflected onto the patient so that we can see where our X-rays will go. And then X-rays are electrically neutral. They don't have a positive or negative charge, and light is not that way. And then just as a side note, X-rays and electrons are not the same thing. Electrons are negatively charged particles. X-rays do not have a charge. So a few more of these. X-rays cannot be accelerated or be changed direction by a magnet. So we can't take them and make them go faster than the speed of light. We can also not change their direction by sending them through a magnetic field. X-rays have no mass. They travel at the speed of light in a vacuum, meaning with no air resistance that to interact with, they will still travel at the speed of light. They can't be focused by a lens. That's one thing that light can do that X-ray cannot. So if you think about our like Pink Floyd album covers, you're going to take that normal white beam of light, turn it into a rainbow. X-rays don't do that sort of thing. They don't change direction when sent through a prism, that sort of thing. And then X-rays form a heterogeneous beam. We'll talk about this in a couple weeks. But essentially, heterogeneous hetero means different. X-rays, when we make them, they don't all come out at the same energy level. They're going to have a bunch of different photon energy levels. X-rays travel in straight lines. That's an incredibly important one that we'll use kind of as the basis for a lot of concepts down the line. And then there's some kind of fringe, less important ones here, but X-rays can cause some substances to fluoresce. Essentially, when you X-ray a substance and then it produces its own light after having been stimulated by X-ray, that's what we call fluorescence. And then X-rays can be absorbed or scattered by tissues in the human body. Light doesn't really get absorbed except for high energy ultraviolet radiation can absorb into your skin cells and damage your tissues. And then X-rays can cause secondary radiation. This is our scatter. That's when an X-ray comes in, hits a body part, and changes direction. Light doesn't do that. It can be reflected, which is not the same concept here. And then X-rays can cause chemical and biological damage to living tissues. This one is something that X-ray and light kind of shares. And then moving on, this will be kind of closing the rest of the lecture. We're at 36 minutes, should be done by 45 or so. So electricity, we produce X-rays using electricity. So it's an energy change form. So we're starting with electrical energy. We're going to finish with electromagnetic. So what electricity is current that's produced when a negative charged electron flows towards a positive charge along a wire or other conductor. We have three things that kind of factor majorly into electrical factors. The first one would be resistance. It's any part of a circuit that slows down the flow of current. So we have electrons flowing through the circuit. Anything that slows or stops those electrons causes resistance. We measure that with what we call an ohm. It's an omega symbol. Basically, I'll kind of draw it with the mouse. It's line up to a circle, line going out this way. Sorry, it doesn't show up on the screen. Not very important. Current. So this is the quantity or amount of electrons flowing in a circuit. So it's how many electrons are we sending through that wire. We measure that in amperes, which is just a capital A. We'll call them amps here. And then when we talk about electrical factors relating to current, we're probably going to end up using milliamperes, or M large A, sub M large A. And that's 1/1000th of an amp. That's what the prefix milli means, 1 over 1,000. And then voltage is electrical potential energy or potential difference. So voltage is kind of the most confusing one. It's the one that basically says the electrons on the starting part of the circuit, how badly do they want to get to the end part of the circuit? So it's this idea of the top of the roller coaster and you're just about to go down, and you know that roller coaster has potential energy because once you push it forward, it's going to severely drop and fly down the track. It's the same concept here. So the higher you are, or the more voltage you have, the more potential difference there is between the start of the circuit and the end of the circuit. So the higher the voltage, the faster those electrons will flow through the circuit. We measure it in volts. In X-ray, we actually deal with higher amounts of voltage than we do with amperage. So we're going to deal with kilovoltage. Kilo is the prefix meaning 1,000. So 1 kilovolt is equal to 1,000 volts. Kilo means 1,000. Potential difference, there's a couple different words we can use, whether it's force or strength of the electron flow. We also use speed is an easy way to try to understand it. So it's the force, strength, or speed of the electron flow in the current, and it's measured as volts. Again, force or speed of electron flow. So different household appliances are going to need different voltages depending on how much heat they generate or how much voltage they need in general. So your dryer, which is going to have to create a bunch of heat to dry your clothes, needs 220 volts. That's why you have a special plug for a dryer in your home. And then pretty much every other household appliance is going to just need 110 volts. So your television, the computer I'm plugged into right now, your phone charger, those all use 110 volts. And then the volt, specifically its definition, not very important, but it's the amount of current needed to flow in a circuit with a resistance of 1 ohm. So for an electron to get through a circuit that has a resistance of 1 ohm, it needs to have at least 1 volt. That's how we measure it. And then we have two different types of current. We talked a little bit about this last week, and we're coming back to our word roots for negative and positive. We have alternating current and direct current. I drew a graph last week. There's a few more graphs here that kind of give you a sense of what we're talking about. But direct current is flow in one direction. So those electrons are only going to flow from the negative end of the circuit over to the positive end. Alternating current's the opposite. So they're going to flow from the negative end over to the positive end and then back and forth, kind of in like we draw a curve or a graph that looks a lot like this to show what alternating current looks like. So a good example of direct current is a battery. So a battery provides constant positive charge at the anode. Anode is the negative end, and negative charge at the cathode. And what that does is it causes current to flow constantly from that cathode, the positive end, over to the anode. And we call that type direct current. Alternating current is the opposite. So it's flowing back and forth from cathode to anode, back and forth, back and forth, back and forth. And we draw a nice, what we call sine curve graph to demonstrate that. So the electricity provided by your public utility, Rocky Mountain Power, whoever it is different. It flows at an alternating rate, meaning it switches from positive to negative. And it does this at a regular interval. This is where frequency is going to come back into the equation. In the United States, we use an electrical frequency of 60 hertz or 60 times per second, and then 120 impulses per second of positive to negative. We say that different for a reason I'll show you on the graph in just a second. And so generating X-rays, we need to only have positively flowing electrons. So we end up with this issue where we have the X-ray machine plugged into an AC outlet that's giving us 220 volts, but we need electrons only flowing in the positive direction. So what we have to do is we take this alternating current from the wall outlet and we have to turn it into direct current inside our X-ray machine. And we do that by a process called rectification. Rectify means to straighten. I know it's kind of a weird word to use here. But what it does is a normal, and I'll kind of give you a sense of what this graph is showing here. We have time. So as these electrical pulses flow back and forth, it's just showing across time the pulses. And then on the upside, and they neglected to draw the downside on this graph particularly, but this is P for positive voltage. So this is the neutral part of our circuit. This would be direct current here. But what we're doing is we're having electron flow in the positive direction and then back towards neutral. And what would happen here is it would continue down in the negative direction and then back to neutral, up to positive, back to negative, positive, negative, positive. And that's alternating current, alternating between positive and negative voltage. I know it's not drawn here. I apologize. So what we do when we rectify is we convert alternating current to only positive impulses, which is what we call direct current. So a normal alternating current graph is going to have another like upside down cup right here showing the negative portion of the phase. And what we do when we rectify is we take that and we flip it upside down. So we have only positive voltage impulses. And that's to keep our X-ray tube safe for a reason we'll talk about in a couple weeks. So it's not exactly the same as DC power. Since it's not a steady flow, it's more of a pulse. You know, it's kind of positive, positive, positive instead of up here and then stays positive the same way that direct current works. So it's a pulsating flow, but it's all positive instead of both. And then last concept we'll talk about here is electromagnetic induction. I understand these are very foreign concepts. It's probably kind of frustrating to try and learn them in this way, but it's really just trying to understand the rules and the definitions here. That's all you really need to know. So induction is this kind of two-way process where electron flow creates magnetic fields, and then if we move circuits through magnetic fields, we create electrical flow. That's kind of all you really want to know about induction here. It's a two-way process though. So one, up to magnetic fields. Second, magnetic fields create electrical flow. So it goes both ways is essentially how it is. So we have something called the right-hand rule. Basically what that means is if you move a magnetic field, and this is a magnet, north end, south end, positive, negative, there's a magnetic field that's kind of shaped like a I sound like a fat kid. Nutter Butter, the cookie. You know, it's kind of shaped like almost like a bow tie with rounded ends. That's what magnetic fields look like. When they create a magnetic field, they have little areas around them called lines of flux. Let me pull up an actual picture of that to demonstrate that concept a little better. Just give me one moment. That's a terrible picture. That's also terrible. That's better. So these are our magnetic lines of flux. So you have the north and south end of a magnet, and the magnetic flux lines are the lines of attraction between areas when two magnets are in consideration here. So a south end attracted to this north end, and not attracted, or essentially attracted in this way as well. But since they're attached, it doesn't matter. So what you get is these flux lines, and those are what we're using to think about this magnetic field. So you're imagining kind of these lines around this structure that are looking a lot like a cookie. So what happens with this right-hand rule is if we move a magnetic field past a conductor is this area of wire, coiled wire, just concentrates the amount of interaction between the flux lines and the wire, and vice versa. So vice versa meaning we would move this current or conductor past the magnet. It's going to create a magnetic field. So if we move the magnet, as you can see the arrow moving it towards the conductor, the voltmeter or current meter shows 0 here, or a small amount. As we move it closer, it starts to produce a bigger electromagnetic field here, and it would also stimulate flow in the wire. So the two things, so electricity flowing, which is through here, is going to create a magnetic field, and then magnetic fields passing through or by a wire are going to create electrical flow. So it goes both ways is kind of how this works. So we use this concept in the X-ray circuit, and this one's particularly complicated, but there's just some rules here. I'll point them out to you, and that's what you're going to want to know. We talk about transformers. There's a couple in the X-ray circuit that are important. Transformers are a technology based on induction, or a process we just talked about, where electrical flow creates magnetic fields, and then moving moving wires through a magnetic field creates electrical flow, are used to convert voltage and current to larger or smaller values. So what we get when we take the power from a power or public utility and plug it into our X-ray machine, we're getting 220 volts. And if we go back to voltage electrically, we use thousands of volts, kilovolts. So what we need to do is we need to take those 220 volts and we need to convert them to much higher values, which are our kilovolts. So what we do is a transformer, and we're going to talk about step up and down. I want you to key in on the fact that up and down refers to the voltage. There's going to be a confusing situation on step downs where we're increasing current, but I want you to know that the down, even though it's increasing current, refers to voltage. So step up and down refers to voltage. What a step up transformer does is it has more windings on the secondary than the primary. We'll talk about that here in a second. We use a step up transformer to increase voltage. So that's where we have our 220 volts coming into the wall. We throw it through a step up transformer, and that gives us much more voltage, kilovoltage, on the secondary side. And then a step down transformer is the opposite. Has more windings on the primary side. Again, don't worry about that for now. We use that to increase current by sacrificing voltage. So you'll start to see current and voltage are in an inverse relationship. We can give up some voltage to increase our current, or we can give up some current to increase our voltage. So a step-up transformer increases voltage and decreases current. A step-down transformer increases current and decreases voltage. And this one has less windings and less voltage on the secondary side. So what we have when we talk about windings, they go around an iron core. Iron core is a great conductor, and it enhances the electromagnetic field around them. So we have these windings where we take our primary side wire. This is our 220 volts coming into the X-ray machine, and we wrap them around part of this transformer, and there's windings around this. So you can see this wire comes in, wraps around again, and goes back to where it came from. And then we have a primary and a secondary side. This would be a step-up transformer. because it has more windings on the secondary than the primary. Essentially, what's happening here is, going back to induction, we are sending current through this wire, which we know by induction creates a magnetic field. And what that magnetic field does is it goes through the iron core, and we know the opposite portion of induction is that magnetic fields create current based on the amount of wire. So we come in with primary voltage, send current through the wire, it creates a magnetic field which is enhanced by the iron core on the transformer, and that magnetic field travels through the iron core to the secondary side. And our opposite portion of induction means that electrical flow is going to be stimulated by this magnetic field inside of the iron core. And the high amount of magnetic field combined with the high amount of windings means we're going to create a lot more voltage on the secondary side. So, step-up transformer, things to know. Primary side has less windings of wire than the secondary side. And what we get in the step-up transformer is a higher voltage and a lower current on the secondary side. So, again, for review, step-up transformers have more windings on the secondary side, you can see all these here, and less on the primary side. This is how we're going to get our kilovoltage. This is used where high voltage is needed in the X-ray tube to take our incoming 220 volts from our public utility, whatever it is, and turn that into thousands of volts that we need for X-ray. Secondary type. This will be our step-down transformer. Down referring to voltage. Has more windings on the primary side. You can see 1, 2, 3, 4, 5, 6, we'll say 20 and 10. It has a lot more windings on the primary side than the secondary side. And this is used where we need lots of current or electrons. We'll talk about that later. It's the cathode, long story short. Step up, increase voltage, more windings on the secondary. Those are the two things to know. Step up, voltage, more windings on the secondary. Step down, more windings on the primary, and used where we get high current. So what we do with both of these, and we use both of these in the X-ray circuit, is that we increase the voltage in one place in the circuit, and we are going to lose current there. And then the other one, we're going to take our incoming 220 volts, and we're going to give up some of that voltage so that we can get more current, milliamperes. So when one goes up, the other goes down. That's just coming back to that inverse relationship that we have with voltage and current. All right, and that's all for that lecture. I'm going to record another one for the upper extremity positioning that we'll talk about here in just a second. Okay, so we're back. What we were supposed to talk about on March 18th was going to be Chapter 4, which we just went over, and Chapter 13, which refers to the upper limb and shoulder girdle, so everything from fingertips to the scapula and collarbone. We're going to just talk about anatomy in this lecture. I'm going to upload a second lecture for what we would normally talk about on March 19th, which would be the Thursday class, which is our positioning class. And in that lecture, we're going to cover from the fingertips to the elbow joint. And then the following Thursday, we'll talk about elbow, humerus, shoulder joint, scapula, and clavicle. So for now, we're just going to talk about anatomy. We're going to talk about how we name joints, at least in the hand. Then we're going to learn some bones in the wrist that can be difficult to deal with. Some joints here as well, and then an elbow joint. We'll actually talk all the way up through the clavicle for this lecture. So, upper limb and shoulder girdle. Shoulder girdle refers to the scapula, or the shoulder blade, the collarbone, and then kind of how the humerus attaches to it. And then humerus is the bone from the shoulder girdle to the elbow. The elbow is a joint between the upper arm and the forearm, or the humerus and the radius and ulna. And then the wrist is our collection of small short bones that allow for a lot of movement and attach our hand to the forearm. So it's basically group of joints, long bone, joint, long bone, joint, long bones again. This is just kind of our formula for the upper extremity. So we're going to call fingers digits. We're also going to call toes digits. I'm going to get metacarpal and metatarsal mixed up a ton, so just do your best to make sure you know what's on the screen when I say it wrong. So we number them 1 through 5. So think about anatomic position, hands down at the sides, palms facing forward. They're going to be numbered 1 through 5, starting with the thumb. So thumb is number 1, Index finger is number 2, middle finger number 3, ring finger number 4, and then the pinky is number 5. So digits 2 through 5 consist of 3 phalanges. Phalanges are the singular bones that form, ignore that I put the mouse over that. Phalanges are the single bones in the finger, and we have 3 of them in digits 2 through 5 out here. The thumb is different. So we're going to have a proximal, meaning closer to the point of attachment, a middle phalanx, and a distal phalanx, distal meaning further from the point of attachment. And we're going to have that on 2 through 5. And then the thumb is going to be different. It only has a distal and a proximal because there's only 2 phalanges instead of 3, as you can see. The way that we're going to name the joints between each of these is going to call them interphalangeal joints. So phalange and then a joint between 2 phalanges will be an interphalangeal joint. So we're going to have, the way we name those joints is going to be naming them for how close the joint is to the point of attachment. So proximal phalange, interphalangeal joint, middle phalange, interphalangeal joint, distal phalange. So we're going to name this the proximal interphalangeal joint, or the PIP joint, PIP, proximal interphalangeal. And then we have a dip joint, distal interphalangeal. And that's how we name those joints. So again, proximal phalanx, proximal interphalangeal joint, middle phalanx, distal interphalangeal joint, and distal phalanx. And then in the thumb, we just have an interphalangeal joint, and then proximal and distal phalanx. Well, that's pixely. So the bones of the hand in the actual palm of the hand, the way we think about it, are going to be called metacarpals. Meta meaning above. Carpals are the bones in the wrist. So that's how we name those. They're also numbered 1 through 5 in the same convention. So the one at the base of the thumb is number 1, and then pointer finger 2, middle finger 3, index or ring finger 4, and pinky 5. We're going to have some names actually for the particular points on the joint as well. So the distal end out towards the phalanges is going to be the head of the metacarpal. And then we have the body, or the shaft, and the base. The base attaches to the carpals, or the wrist. So we're going to have a joint between the metacarpals. Theo, quiet. We're going to have a joint between the metacarpals and the phalanges. That's going to be our metacarpophalangeal joint. And you'll start to see... Hey! Okay, now that the hounds have been silenced, again, distal, head, body, base is the proximal. So we're going to name the metacarpals and the phalanges. The joints between them are metacarpophalangeal joints. So you start to see a pattern with the way we name joints. And this is an important concept to pick up if you want to kind of be able to just name a joint based on what you know and not have to memorize it. The way that we name joints, at least in the extremities, are going to be naming them with the name of the proximal structure first, metacarpo, and the distal structure second, phalanges. So metacarpophalangeal joint. These are going to be interphalangeal joints. I know that's not helpful because they're the same thing. The next joints between the wrist and the metacarpals are going to be metacarpal joints. As we move down, we're going to have a joint between the radius here and the scaphoid here would be a radioscaphoid joint. So naming them proximal to distal. So metacarpal, metacarpophalangeal. And it's going to be the same way all the way up to the shoulder. And that might help you name them as we move forward. And then these small sesamoid bones that are in the wrist, they're kind of in the thumb as well, are going to help protect the tendon. That's something we'll see kind of as we go forward and look at thumb x-rays tomorrow. Sorry. So moving down to the wrist, we also call it the carpus. The bones themselves are called carpals, and there's 8 of them. We kind of arrange them into rows. They're more of arcs, as you can see here. This one's less of an arc, more of a row. But we have a proximal row, which is close to the forearm, and a distal row close to the metacarpals. So thinking lateral to medial, this can be kind of confusing because when we think of anatomic position, the fingers are pointing down to the floor. So this out here is our lateral side. This is the base of the thumb. So distal out towards the fingers. This is our distal row, proximal row. So moving lateral to medial over here, we have the scaphoid, which is a very large one, commonly injured, lunate, which is a large one at the base of the joint, and then triquetrum and pisiform. I wish they had easier names for you guys to memorize, but this is what we're stuck with. And then we have a distal row of metacarpals as well, and we also name them lateral to medial. We have trapezium and trapezoid. Trapezium's what they put an elephant to stand on in the circus, so it kind of looks like that, like an upside down cone funnel type thing. That probably won't help you. And then trapezoid. Capitate is the enormous vertically oriented one in the middle, and then the hamate, which is kind of hammer shaped. You can kind of see the handle and then the club of a hammer. That might help you. Not sure. So, notable details. The scaphoid is the most commonly fractured bone. The capitate is the largest, the one big one in the middle. And the hamate has a little hooked projection called the hamulus. And that's an easy way to notice it if you don't memorize the thing I have on the next slide. So, we have a little mnemonic on the next slide. Not exactly the most politically correct, but it's definitely going to help you remember it, because it's not about what's correct, it's about what's memorable for things like this. So the way that we do carpals, this is thinking proximal row, medial to lateral, distal row, medial to lateral. Some lovers try positions that they can't handle. So working proximal, lateral to medial, and distal lateral to medial. Some scaphoid, lovers, lunate, triquetrum, positions, pisiform, and then this one not so helpful, but that, trapezium, they, trapezoid, can't, capitate, handle, hamate. And then to kind of work this out, the trapezium, is at the base of the thumb, So looking back here, the trapezium, the most lateral bone in the distal row here, is at the base of the thumb. So that's the one way you can kind of separate this little confusing difference here. So normally I'd have you guys label these. Having just learned them, we won't worry about it. But 1 would be the base of the 5th metacarpal, working down to 2 is our scaphoid, 7 is a portion of the scaphoid, 3 is our capitate, the big one in the middle, 4 is the hamate. Moving over to 5, this is the trapezium at the base of the thumb, 6 is our trapezoid. In an x-ray, things get layered on top of each other. So this is our trapezoid underneath the trapezium. Not exactly the most pretty thing you'll see. 7 we talked about. 8 is our lunate, the big one that kind of forms the joint with the radius down here. 9 is our, excuse me, sorry, triquetrum. And then 10 is the pisiform, kind of labeled over the triquetrum. 9, triquetrum again over here. Kind of drew a blank there. And then 11 would be the base of our 2nd metacarpal, and 12 is the, I don't know what they're trying to show there. I guess maybe the hooked projection on the hamate here. And then we have little styloid processes on the ulna and radius. So ulnar styloid, radial styloid. So things that the wrist can do, because it's a collection of those short bones, we talk about deviations. So we have anatomic position, where the hand is here in neutral position, and the radius on the medial side or lateral side of the bone, and then ulna on the medial side. We can deviate the hand by tilting it out one direction or the other way. So tilting the wrist out towards the ulna, which is on the medial side, is ulnar deviation. And then radial deviation is tilting the wrist towards the radius. So those are 2 ones that we use for x-ray positioning, so they're important. And then we can also flex the wrist, which is to bring it anterior from anatomic position, and extension is to bring it posterior from anatomic position. Talking about the anatomy of the distal forearm for the radius and ulna. The ulna is the longer, thinner bone, so you can kind of see thinner all the way out to the end of the wrist. It's on the medial side, so this is anatomic position. This would be a right wrist with the thumb lateral. And the radius is the slightly thicker and slightly shorter bone, which just sits on the lateral side. Thumb is on the lateral side on anatomic position. They both have little styloid processes, so styloid process on the ulna, styloid process on the radius. And then we have 2 motions that the forearm can do that the lower leg cannot do, and that would be pronation, which is to rotate the radial head around the elbow joint to bring the palm down on the table. Causes the radius and ulna to cross over, so they form sort of a long, tall X here. And then supination is what you see here. The bones will not be crossed, and that's turning the palm upward towards the ceiling. This is how we x-ray the forearm, at least in a supinated palm position, so that the bones don't get superimposed or crossed over, like you can see in a picture that we'll talk about tomorrow night. And then the proximal forearm, up by the elbow, a little bit more complicated because we're having two joints formed with the humerus. So the radial head joins with a structure called the capitulum of the humerus. And that's this area right here, kind of a rounded spot for this thing to pivot around. And that forms the humeroradial joint, again named proximal to distal humeroradial joint. There's a little lumpy boy right here called the radial tuberosity, and the biceps come down the arm, attach right there. When you flex them, they bring the elbow up. They flex the elbow joint. And then you have an olecranon process, which is on the back of the forearm. You can't see it right here. And that's kind of your funny bone, that bone on the back of your elbow close to your ulnar nerve. When you bang it, it starts to hurt really bad. That's your funny bone. The proximal ulna here joins with the trochlea. Trochlea is a word for kind of pulley in Latin, or something that gets pivoted around, at least, of the humerus. And that's this structure right here, the kind of white bow tie shaped thing here that kind of runs around the back of the ulna, or the humerus, excuse me. And then we have a little area inside the ulna, if we look at it in profile, and we'll look at this again. We call it the semilunar notch. I usually like to demonstrate this by showing it to you on the skeleton. Maybe you can pop on Google and take a look at that, or see it in your book. So we have the semilunar notch, and we'll see if it's here. No, it's not. I'll find it on Google real quick. So what I have here is a picture of the ulna pulled away from the rest of the bones in the elbow. So olecranon process, this is the big rounded back portion of your elbow, and that sits kind of superior to this semilunar notch. We call it semilunar because it looks like half a moon. Semilunar, lunar meaning moon. And that trochlea of the humerus kind of just fills this space. And then there's a little radial notch where the head of the radius sits in there, and then a coronoid process on the anterior. So working our way back here, this coronoid process is this front part right here, kind of works its way around the back to the olecranon back here. And that's how we're going to name this. Semilunar, looks like a little moon. Then the distal humerus, as far as little bone landmarks go, is probably the most complicated. Again, I like to have the skeleton here so I can show you how when we flex the elbow, the coronoid process goes into the coronoid fossa. When we extend the elbow, the olecranon pushes into the olecranon fossa. We'll just have to make up for lost time in a couple weeks if we're allowed to meet again. So the distal part of the humerus, we have condyles. Condyles are a raised structure on bone, so you can see them here and here. And then we have, and their muscle attachment points. And then we have epi, meaning above condyles. So lateral epicondyle and medial epicondyle here. These kind of are the palpable parts of the elbow. So if you feel, when you bend your elbow, you feel on the sides of the elbow. You can kind of feel pointed parts of bone. Those are our epicondyles. On the posterior part of the humerus, so opposite this side right here, we're going to have an olecranon fossa. That's where the olecranon process goes into when you extend the forearm or straighten the arm. Then we have a coronoid fossa on the front here, which is when you fully flex the arm. That little pokey part on the front of the ulna is going to go in there and stop the arm from continuing to flex. And then capitulum and trochlea, the points where the radius and ulna articulate. The capitulum is this little rounded portion, which is where the radial head attaches. And then there's the radial fossa just above it, which does the same thing the coronoid fossa does when the elbow flexes. And then the trochlea is this other portion. You can kind of see, this is from the anterior, we're looking at the humerus. You can kind of see it wraps around, and this is a posterior view to show back here as well. So the trochlea is kind of like a pulley system that semilunar notch slips on top of and kind of lets it hinge around it. And that's the articulating, meaning joint forming surface for the humeral-ulnar joint. So two technically different joints, humeral-ulnar for the ulna and humeral-radial, again named proximal to distal. And then moving up the humerus to the proximal portion where the shoulder is, we have a head of the humerus, which is the rounded portion that forms the ball portion of a ball and socket joint. This is the posterior humerus, anterior humerus, front view is what that means. And then we have two necks. We have an anatomic neck, anatomical, which is kind of the transition point between the humeral head and the rest of the bone. And then we have a surgical neck. The surgical neck is named kind of in a fun way. It's the most common axis, I guess you could say, that this bone breaks. So when the humerus breaks, it's most likely to fracture at the surgical neck. It's kind of an easy one to pick up on. And then two important landmarks where the lats, the muscles that you would do pull-ups with, attached to, as well as the rotator cuff. You have a greater tubercle, which you can see best from the front view, is this superior, more lateral, raised portion of the bone, a couple of rotator cuff muscles attached there. Then you have a lesser tubercle, which kind of, if you're looking dead on at the humerus like we are here, it kind of looks straight at you. It's on the very anterior part of the bone. And we rotate the shoulder differently to see these differently for shoulder x-rays, which we'll talk about, I think, the week that we would have class on the 26th. Moving on, the shoulder girdle itself. So now we're considering, this is from the anterior, this is from the posterior. Shoulder girdle considers the clavicle, the scapula, and then the proximal humerus. So scapula we also call the shoulder blade, clavicle also called the collarbone, and then the proximal humerus, that's our ball for our ball and socket joint. Scapula is kind of a very weird, flat, irregular bone. It has three borders, so what we're looking at here is looking at the bone from the anterior, ventral meaning the belly or anterior surface. We have a superior border with a superior angle, a medial border, the spine would sit kind of in this orientation here, and then an inferior angle and a lateral border. At the lateral angle, kind of think of a triangle, so angle, 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 border, border, border. At the lateral angle, we're going to have something called the glenoid cavity, and that's the socket for our ball and socket joint. And that's kind of where the humeral head attaches to. Again, this is looking anterior at it. Now we're looking posterior. So on the posterior view, you'll see something called the spine of the scapula. It's a ridge of bone where the on the posterior scapula where muscles attach to. And then we have three processes at the lateral angle. We use all of them for x-ray. We have the coracoid, which is where we position for a chest x-ray, or sorry, not a chest x-ray, a shoulder x-ray. We have the glenoid fossa, where the joint between the glenoid and the humerus is formed, glenohumeral. And then we have an acromion process, which is where the collarbone attaches to the acromion. The acromion is large, it's rounded, you can kind of see it from the back here. This is an actual bone you can kind of see. And that joins with the clavicle at an acromioclavicular joint. This is where the naming conventions for joints get a little bit weird. It's been very simple so far. We've named them proximal to distal. But technically we're working medial to lateral when we talk about the acromioclavicular joint. So this one is named backwards, if you ask me, because this would be the most proximal point of attachment, because this is where the appendicular skeleton meets the axial skeleton. So AC joint or acromioclavicular joint is a little bit backwards. So we're naming it acromioclavicular instead of clavicular or acromial. Just maybe it's the way they attach. The words don't really work well together there. And then we have a coracoid process, the pointy one anterior. It sits anterior and medial to the acromion. You have a couple of biceps muscles that attach here, and then the pectoralis minor attaches there as well, if you're interested in those sorts of things. And then the glenoid process has the cavity where the humerus attaches. And that's how we form the glenohumeral joint. This one, at least, is named in the same way that the rest of the extremities are. So gleno, closer to attach of a point of attachment or proximal, and distal, the humerus, glenohumeral joint. Moving on, for the clavicle, the last thing we talk about, doesn't have a lot of exciting landmarks. Has a medial and lateral end. The lateral end meets with the acromion at the AC or acromioclavicular joint. Then the medial end forms a sternoclavicular joint, and that one's named a little bit more sensical because it's proximal to distal attachment point, sternoclavicular. We also call the clavicle the collarbone, and again, it has two joints at the medial and lateral side. For x-raying the shoulder, kind of what we think about and what we talk about, in the specific ways where we want to. We're going to use one cassette per exposure. We are x-raying long bones. You usually can't fit two onto one. And then I guess another consideration here would be we don't really use the old school types that can only expose once before they need to be read. And then sometimes for long bones like the forearm, the humerus, as we move to the leg, the tibia, the femur, they're going to probably need two pictures. So you'll do a proximal picture. Let me go up a little bit. You're going to do a proximal picture that's going to show maybe most of the upper humerus to maybe just about the elbow, and then you'll have to do a distal picture as well. So that would be two pictures AP and then two pictures lateral, which is different than most of the things we do. When we x-ray around the wrist, we want to remove everything that we can from the wrist. Same thing from the fingers, rings, if they can come off. Lots of people, they come to you and they say their wedding ring hasn't been taken off in 20 years. Today's not the day. It's not going to be worth it. And then for shoulder x-rays, the adjustment clips on the straps of bras that go from the cup to the clipping in the back, those are going to show up. So you can drape them down off the shoulder or completely change the patient. That's two ways to go about that. And then shielding, you can shield center mass if you're looking just at the shoulder or the arm or the fingers. So it's better to just do it. It makes the patient feel better. It can potentially reduce the radiation dose. There's some controversy about shielding right now in this profession, but until there's anything concrete about not continuing to shield, just if you can, you should, is kind of how that goes. So tomorrow night, I will try to get a lecture uploaded on positioning of the hand, fingers, wrist, and forearm, and we'll get that up for you tomorrow night. Anything else to say? I don't think so. Hour and 15 minutes, that's significantly less than we would normally spend in class, so hopefully you feel like this is a better use of your time. Happy to receive feedback from you guys. I know this is a lot of me talking and you just kind of watching, and I'm not taking the normal breaks that we would take in class to answer your questions or to give you time to write and take notes. So, just pause the video if you have to. Work through it at your own pace. And I'm gonna set up the announcement underneath this as a discussion. So if you do have any questions about this lecture specifically, feel free to let me know. Your classmates may be able to answer your question. I think that's a great way to learn as well. And if you have any questions specifically for me, I'll be in there as well, answering whatever you guys might have to ask. So just let me know. I know this isn't as good as us meeting in person, but I'd like for you guys to still be able to have my input on the material, so this class doesn't go fully online until the world ends. I mean, today we had an earthquake, so happy apocalypse. I'll talk to you guys soon.